Welcome to this course of computer design of electrical machine. We have a lecture 26 on design of brushless permanganate machine part 1. Will I have a outline of presentation with the introduction, history of permanganate brushless motors, then application and permanganate motor configuration, then permanganate material and magnetic circuit, and exercise and numerical problem followed by references. Now coming to introduction, the permanganate machines use permanganates in place of wound field excitation, and this enables a more compact, simpler and more efficient machine. As you can see in the typically in the photograph, high energy density permanganates and development of power electronics started the permanganate brushless machine era in late 1980. The permanganate brushless motor may have rotor of permanganate in place of electrical excited or wound field rotors, and availability of high energy density permanganate has made the permanganate brushless motors possible with the higher power rating. And permanganate brushless motors are classified on the basis of their induced EMF wave shape like sinusoidal or trapezoidal, and sinusoidal type of known as permanganate synchronous motor or sine fed motor, and permanganate brushless DC motor also known as a rectangular pole or PML DC motor. So, use of permanganates in the construction of electrical machines brings the following benefits. No electrical energy is absorbed by the field excitation system, and thus there are no excitation losses, which means substantial increase in efficiency and higher power density and or torque density than when using electromagnetic excitation, and better dynamic performance than motors with electromagnetic excitation, and simplification of construction and maintenance, and reduction of prices compared to some type of machine. Now, permanganate machine has the following advantage: higher possible efficiency among all type of electrical machine, higher torque to weight ratio, higher power density, lower inertia, low maintenance requirement, and compact design. Now, coming to about history of permanganate brushless machine. So, first permanganate excitation system were applied by electrical machines as early as 19th century, with the example as like J. Henry in 1831, H. Pixey in 1832, and W. Ritchie in 1833, and F. Watkins 1835, and D. Davenport 1837, and M. H. Jacobi 1839. And magnetic material used was steel. So, of course, the use of very poor quality hard materials, steel or tungsten steel, soon discouraged their use in favor of electromagnetic excitation system. And now coming to various form of permanganate or electromagnetic devices through history. Here it is a typical example on left side, the barrow wheel, the teeth of the wheel W dip into the mercury between the poles and of a horseshoe magnet, and when the current flows through the wheel. And of course, on the right side, the Pixey generator which was put in 1832. This was the first device in which the multi-turn coil was used to increase the electromagnetic effect. Now, typically coming to various form of permanganate and electromagnetic devices through history, that William Sturgeon, he given a reconstruction of Sturgeon motor. The rotor consists of two horizontal bar magnet as shown in the photograph, which rotate past the poles of four electromagnets, and these are connected through a commutator which consists of two concentrated jars of mercury, four sliding contact, and the contact is divided into four typically quadrant. And the Ritchie rotary motor, which I already discussed earlier about the history, the current is supplied to electromagnetic north as pole through the mercury in the two semiconductor groove as in baseboard, and the motor will rotate in the earth magnetic field, and starting the Becker electrically coupled motor vehicle. The horizontal bar magnet is the rotor, and its motion is transferred to the wheel by gearing, and is powered by a galvanic battery. And typically Thomas Davenport, the constructor of one of the Davenport motor. So, Davenport motor in 1837, the rotor carries the four coils on the cruciform frame, and the stator consists of a two semiconductor permanganate, semicircular permanganate with the like their poles adjacent, and also referred as father of typically as a DC motor. And typically Jacobi, motor which he invented in 38, motor rather similar to this one, but with the permanganate, was used by Jacobi to propel a boat of the river Nevada at St. Petersburg. And of course, this is another Grammer generator with the pond field on modern DC and PM motors. Then another cut way of early Siemens generator that was used as a motor. Then the invention of Alnico in 1932 received power grid excitation system. However, its application was limited to small and fractional horsepower DC converter machine. At present time, most PM DC motors with slotted rotor use the Faraday magnet. Then this is typically the Alnico, use of Alnico in 1935 in various electromechanical devices. So typically Alnico, you can see the photograph of Alnico horseshoe magnet, and the assortment of Alnico magnets used for various application including PM motors in 1956. So advertisement by Jaguar Radio Manufacturing Company for Alnico 5 loudspeaker in 1945. As illustrated, Alnico 5 was allowed a dramatic reduction in size and weight of magnetic needed to produce the equivalent flux from 2.5 kg in 1930 to 0.13 kg. And of course, the research for Apollo mission at NASA in 1960 led the fast track of development of magnetic material and use of soft magnetic material in the onboard computer memory for rope memory named as Apollo Guidance Computer in 1966 and developed by MIT and Raytheon, as you can see in the photograph. And then typically the Hall effect brushless motor, typically here, so that was developed by Kraft. Development of brushless DC motor with electron combination used in photo switches, photodiodes, and display ferret with the Hall switch of current. The use is a prime mover for life support blower, oxygen circulation in the lunar portable life support system. And then typically strange aerospace requirement for brushless DC motor have resulted in new and improved drive system, torque motor and servo motor, and variety of console, as you can see in the photograph. And this is typically how the history have been for this evaluation of brushless DC motor from 1930 to 1975, typically, which NASA have reported in 1975. So now coming to many company develop brushless product as magnets and electronics improved for the next 20 years. By 1980, brushless DC motor became favorable for emerging computer peripherals product like printer, tab driver, floppy disk drive, hard disk drive, driver for letter CD and DVD. As you can see in the photograph, how it is there in the different parts of the, like typically the camera or so for movement, and then the floppy disk drive, as a spindle drive in floppy hard disk, and in different drive it is put this kind of motor like. So in mid 1990, they were called PMAC synchronous motor. The motor were not much different from their DC brushless, but only how they were powered with sine current like AC induction motor. By the year 2000 and beyond, there were many variation motors with PM emerged, including the axial flux, slotless interior power magnet, as well as the surface power magnet rotor configuration for almost many applications. Like, so you can just see how it is axial field motors, radial field motors. Typically axial field motors are there as photograph you can clearly see. Now coming to applications and power magnet motor configuration. So you can see as for industrial application, the industrial drive like pump, fans, blower, compressor, centrifugal, hose, and machine tools, as you can see here, and another for machine tool applications, and servo tools with the photograph. So, or you have a typically automatic, presses on the left side, and then in international transportation system, as you can see lower, and of course robotics application, as you can see below, by different industries. Then the heating, ventilation, and air conditioning system because of energy efficiency. You can see that typically how these systems are put as a HVC and electronic control motor, how it is really, in the final component of these motors, like different construction. So of course, they use information office equipment typically for computer, printer, plotter, scanner. They also use in typically, as you can see, internal diagram of typically of different kind of fans like single phase BLDC motor for the computer fans, disassembled motor, inner resistor and for pole, then printed circuit board for the controller, and external rotor with the 4-pole ring shaped power magnet motor. Then the single phase power magnet brushless DC motor used for computer fans. Then the power magnet brushless motor used in finance servers. You can see the photograph. Then it's also used in fax machine, photocopier, audiovisual aids, and security system, as you can see in different. And then the typical motors, which are for general application, including the with the controllers, and then the reducer application for wide range like robotics, vacuum cleaner, automobile, home appliances, and industrial robot. So various solutions for fans, blower, and pumps by Nidec. And then a refrigerator because of energy efficiency. PM motor used in many inverter fed compressor motors, and blower fans used in refrigerator for circulation by Nidec. Line start interior power grid brush motor for refrigerator company by patented by this Nidec motor. Then in washing machine, for domestic equipment in washing machine, direct drive PM for washing machine, of course because of high efficiency. And then typically the application replacing the universal motor belt pulley arrangement with direct drive, more efficient motor in washing machine. And typically here, as you can see how universal operate and how this your LG direct drive operates for this application, especially for washing machine. Then bathroom equipment like shaver, hair dryer, toothpaste, and massages and other apparatuses. I mean the photograph and how the equipment is there. Then domestic equipment like lawn mowers, pump for irrigation, swimming pools. As you can see the typically motor on the right side with the submersible pump, and the movers, lawn mowers. Then the domestic like toys and visual and sound equipment. Then domestic air conditioner and ceiling fan. I mean ceiling fan now is coming in India itself, around 60 lakh manufacturers. The fans are there by different industries of brushless DC motor fans. Then the industrial ceiling fans, as you can see the typical photographs and the type of fans in the large 8-feet aluminum HV LS fans you might have seen at the airport. Then the domestic industrial fan, exhaust fans. Then the security system, automatic door closure or vacuum cleaners, as you see it here, because of high efficiency only. Then in transportation, for elevator, escalator, people movers, and light railway and trams. Then the aircraft like flight control and electric ship. Then the typically for aircraft, more electric aircraft, full electric craft, and electric ship, as you see photograph. Then coming up electric vehicle like a traction like in e-rickshaw, BLDC for 850 watt used in India, even for 48 volt with 20 ampere hour battery with a current of 45, lead acid battery. Then even with the solar e-rickshaw to go with the motor is BLDC, power grid brushless DC motor in this. Then the e-bike, electric motor vehicle, BLDC of 250 watt. Then the another with the BLDC hub motor with the 250 watt. And then the electric road with the hub motor, as you can see in the tire how it really look like this motor, PM motor in two-wheeler direct drive motor. Then electric vehicle traction system of motor of interior power magnet synchronous motor of 110 horsepower and one peak torque of 190 Newton meter in two-wheeler. Then in four-wheeler electric transport Cellvec Bolt open ampere by power magnet motors of 200 horsepower in this car, and power magnet booster 53 kilowatt by Cellvec Spark another model. Then typically your electric vehicle traction, you can see how the different parts and different motors are there, not only main motor but the other motors also used for auxiliary motors for different parts of it. And your steering kind of EPS motors, there is various type of motor developed for use in EPS system, as you can see the part of these motors also. Then the power tools like drill, hammer and screwdrivers, because they are mainly sometimes you can call it the standard operation with the battery operation, so energy efficiency or efficiency is very important for these tools. Then grinder, polisher and saw. Then electric sanders, hair cutters and grass cutters. Then dental hand pieces, as you can see in the photograph the different kind of motors for. Then the electric mobility and regulation for electric wheelchair. Then electric scooters and the electric for rehab. Then your artificial organ, ocular assist devices, centrifugal blood pumps and cardiopulmonary bypass machine. Then your warfare tanks, then missile control actuation system, missile vehicles, and then the automated sentry guns, then mobile radar system in defense, that power external and naval warfare submarines and warship. Then the typically the permanent brushless motor rated for 36.5 megawatt and 127 rpm for advanced propulsion system. Then your direct drive permanent shaft generator used for cargo container vessels. Then the permanent brushless motors with ring propeller integrated in the rotor used in boat propulsion system, as you see. So now these are the some of the applications. Now coming to PM motor configuration and construction. So in general, all electromechanical drives can be divided into constant speed drive, servo drive, and variable speed drive. So constant speed drive usually apply a synchronous motor along with which can keep the speed constant without any electronics converter and feedback or any other motor when there is less restrictions on the speed or variation tolerance. So a servo system is a system consisting of several devices which continuously monitor actual information like speed, position, compare these values to the desired outcome and make necessary correction to minimize the difference. A servo motor drive is a drive with a speed and position feedback for the precise control where the response time and accuracy with which the motor follows the speed and position commands extremely. As you can see here, this particular operated from microcontroller the motor for this typically of your robotics application. So in variable speed drive, the accuracy and response time with the motor follow the speed command not so important, but the main requirement is to change the speed over the wide range so that it meets the requirement of application. So in all electromechanical drive where the speed and position are controlled, a solid state controller interfaces the power supply and the motor, as you can see in solar water pumping or the pumping system. So there are three types of permanent motors, electromechanical devices like DC commutator motor called PMDC motor used in large number of applications, permanent brushless motor like DC and AC synchronous, and stepper motor. There you can see the classification PM brush DC motor and brushless sinusoidal excitation and rectangular excitation. We also call PMSM or stage stepper and BLDC motor. So here brushless motors fall into the two principal category. Sinusoidal excited, as you can see here, the sinusoidal excited motors are fed from three-phase sinusoidal current waveform and all phase conducted time called sine wave motors or PM motors. Another motor is the BLDC motor. So you can say brushless motor drive fall into the two principal categories: square wave excited motor. So wave shape are rectangular or trapezoidal. The shape is produced when the MF in armature current is precisely synchronized with the rotor position and 2 out of 3 phase conducted time and called trapezoidally excited motors on the right side. So brushless motor drive fall into the two principal categories: square wave excited. So only 2 phase excited out of 3 simultaneous and control is rotation functional equivalent to mechanical commutator in DC motor. This explains why the motor with the square excitation called DC brushless motor. Now coming to typically construction of permanent brushless motor. Permanent brushless motor mainly consists of stator with winding, rotor with permanent and power electronics converter and sensor assembly. To understand the construction of permanent brushless motor, let's compare with this brush DC motor. So here it is a brush DC motor. As you can see, and it is the right side is a permanent brushless DC motor where the commutation here is a mechanical commutation, here it is electronics commutation. Typically. So now typically you can say PM DC motor is fed from the DC source and battery or DC supply for constant speed. PM DC motor, no power electronics is needed. The PM brushless motor in standard application must fed from the solid state inverter because electronics commutation is provided by the power electronics inverter. So this is a comparison between the two motors. So brush DC motor we have a commutator inverter. So for brushless motor we have electronics commutator, and for brush DC motor we have mechanical commutator. Maintenance requirement of course is minimum for the brushless DC motor. Reliability is high for brushless DC motor. Inertia it can be minimized for brushless, and power density is high for brushless DC motor. Heat dissipation is also good as stator winding is on stator, and speed control is must with the solid state controller. So you can just see the permanent brushless synchronous motor for especially electric vehicle developed by General Motors. How it look like with the motor rotor on the typically with the you can call it with the flux barrier and magnet put in the barriers. So it give a high power density as well as the good field weakening features, or you can call it constant power drive for electric vehicle. And this is typically by Auto, another you can say electric vehicle manufacturers. How the magnets are put on the rotor and the stator winding on the stator. Then the typical brushless motor, typically rotor with the PM, rotor on the PM and stator winding on. These are nameplate of course permanent brushless DC motor where the example is current, power and speed. Then another nameplate by typically a permanent brushless DC motor. Then the permanent brushless motor standard, these are the standards of permanent brushless DC motor for IC standard as well as European standard. Then these are of course typically the construction different parts of this permanent brushless DC motor. And the PM brushless motors construction, you can see it's a typically the standard one, and then the special cooling, and then the force cooling, and the cooling standard 4 corresponding to. So there are different kind of special version for cooling as a construction of these motors, like including typically axial field. And so these are the typically the different variety of construction with the cooling arrangement, different kind of cooling standard, and then the exploded beam. Then the typically the brushless motor construction from a industry like from BAM German industry, that how is the different typically the different specification for you can call it the bearing and other part of it. And then the typically the construct example with the bearing data, like so these are the typical bearing data of these motors. Like also, so the permanent synchronous motor for inverter fired construction with the outer dimensions for the standard BAM motors. And these are the dimensions by NEMA format for standard permanent brushless motor. And typically coming to construction of this, we have first the stator as is shown in the figure, laminations, and then of course you have a winding as it is shown here, wound coil, and then put in the winding. So stator is a conventional permanent brushless motor consists of mainly two parts of function: the steel stator lamination consisting from laminated steel and typically reacting flux, and winding coils either copper or aluminum for generation of armature flux. And of course the stator can be classified mainly based on the structure and winding, like structure outer or inner stator or inner or outer rotor, and winding type may be distributed or concentric winding or of main winding of winding types used in permanent motors. You can just see here structure outer or inner stator. You can just see how it looks like your inner stator and how the outer stator, inner stator on the right side and outer stator on left side. And then the stator winding distributed and concentrated winding. So first case is distributed and second case is your concentrated winding, conventional winding, and then the typically in the conventional kind of winding. Then the you can call it the stator. The itself comprise magnetic steel laminations arranged as redact fluxes. As you can see how it looks like a stator steel laminations main flux arrangement observed in radial and axial redacted manner. And this is the typically the flux density plot when got for the design of this machine with the different flux distribution when the rotor is moving, and typically the kind of rotor slot, very heavy rotor slots here with the typically, so a lot of space is given to the stator so that you can have output power, because magnets are of a smaller size to produce a radial good magnets for axial field as well as in radial field mode. Then how your typically axial flux topology is there, how the axial field magnets are on both sides, winding in between, and how it is typically the geometry in these two cases for axial field and radial field motor. Then this is typically your the stator of this, the winding as well as the magnet placement of your axial field motors. Like now coming to the winding methods. So when referring to the winding methods for motor of high level, there are two main ones, direct and indirect winding. The winding methods can directly linked to the insulation system of the motor. So direct winding involve winding the wire directly on the motor stator tube, and direct winding is more constrained in terms of space required, so not too much wire can be fit into the motor itself due to the poles and other component all varying for space in terms of wire are placed on the motor. This means you cannot fit as much wire onto the motor itself due to higher clearances are required between the poles. And key advantage of this winding is, however, it is quite quick and relatively simple, and it's only require only one step process. And another is the direct winding, as you can see, of concentrated winding on the direct drill winding, how it is placed. So another is indirect winding. Indirect winding will involve winding the wires onto the plastic carriers or bobbin, and there will be threading stage along with the second process to install the bobbin on the motor. And the challenge with the indirect winding is the transfer process. The wire needs to be protected during the automation process, which generally can be quite difficult to automate, and this makes the indirect winding more is a manual process overall. Also due to the two-stage process, the VM cost of the motor can be bit lower. So you can just see how the indirect winding is placed on the first former and then put into the really in the motor winding as you can see in the process of this slide. So the common technique of winding of a stator of commutator may include needle winding, shear winding, and linear winding. You can just see how automated winding machines, linear winding method, multiple spool, and then the typically the bobbin, and the finally the machine like. And this is the typically the process how really the winding is put like typically in mechanical equipment, automated winding machine, blind winding method, needle winding for inner and outer typically like also. Then the typically segmented stator tooth for higher fill factors and ease of winding. Then your additivity manufactured stator part, and the rotor. The rotor comprised of a magnetic steel laminations stacked together, redirect field flux, permanent flux, and provide mechanical stability to the permanent. So you can just see how the steel portion is there where the magnets are put into the flux barrier in the different kind of the rotor configuration. So there are a lot of innovation into it where the flux barrier are created to provide the saliency as well as the reluctance torque along with the permanent torque, and that provide the field weakening as a saliency in this case. So you can just see the kind of rotor, assembled rotor showing the permanent and sleeve for protecting them. And you can see the rotor different kind of construction used here, either surface interior buried magnet or surface mounted magnet. Like you can see on the how they are magnet buried or on put on the surface. For lower speed, high speed, we put buried the magnet. So permanent brushless DC motor type owing to the action of PM DC motor. Control of DC motor drive is comparatively simple and same. The control system can be satisfy the requirement of most of application. And for these reasons, the DC electromechanical drive very often turns into the cheapest alternative in spite of cost of DC commutator motor used in agitator, extruder, milling machine, kneading machine, printing presses, coating machine, some type of textile machine, defense blower, and simple machine tool. I mean, they operate with the simple even from the just control rectifier, and then the dual converter, and then the PM typically the 4-quadrant chopper. I mean, these are the of course the how the permanent brushless DC motor. First you have to rectify them, then you have to put the inverter for control of these different kind of motor with these power converters. Like as you can see for high rating, we virtually use even a multi-level converter to increase the rating of the motor, like multi-level converter, cycloconverter drive, and many. And typically like one brushless motor with dual converter open winding to increase the reliability for electric vehicle or many other applications. Like these are typically the how the power converter with the motor indicated motor type, and converter is part of that included into that, so that the size is reduced for some application like electric vehicle also. And the power converter brushless is very form of typically your motor type. And typically the motor for Tesla, I mean how it is among the brushless motor integrated with electronics control and gear in EV traction with the Tesla car. I mean with the gears. I mean here because motor are designed for high speed, so certainly the gears are put into that to reduce the speed, but it's not control the gear changing like also. So you have a typically for in general rectifier, the influencer and the inverter, the power feedback control, these magnet motors. And as already we classified that you can have a line starter inverter fed with sinusoidal reacting excitation, and how the rotor are put with the flux barrier and magnet into the typically this portion like for line start. And this is another classification of these permanent motors: the axial field, radial field, claw type, disc type, and cage less and cage motors like surface mounted insert and interior. Similarly for generator also we have radial field, axial field, because nowadays we are using permanent brushless generators for class type or forest type, maybe in all the I mean the vehicles for the generating system for charging the battery. So you can call it like here different way of arranging the magnets on the rotor has created many types of permanent synchronous motor and brushless DC machine, and some popular and research type of arrangement and their impact on the air gap, flux density, winding inductance, and their influence on reluctance torque is capable of enhancing the magnet generated on or generated or synchronous torque are discussed here. So you can just see how the surface you can call it mounted, I mean the rotor with the stator is there. How we really putting the magnets on surface like Hallback or typically just inserting the magnet into that, and this is used by surface mounted magnet. I see the construction of the couple of motors, how we are putting magnet segments on the rotor like typically, and what is the flux density distribution they are getting from this kind of radial field motor, and with the of course the some harmonics into this floating construction. So this arrangement provides the highest air gap flux density as directly faces the air gap without interruption of any other medium such as part of rotor lamination. Drawback of such arrangement is the lower structural integrity and mechanical robustness as they are directly fitted into the rotor laminations to their entire thickness. The palm magnet in practice are buried into the rotor laminations that provide some mechanical strength, and by using adhesive tape, the magnets are bound to the rotor, thus that reinforcing mechanical strength and magnet combination. So this surface magnetic machine with this arrangement of magnets are known as surface mounted palm magnet synchronous motor. They are not preferred for high speed applications generally greater than 3000, but the machine with very small rotor diameter can be found to have a speed in the range of 50,000. The reluctance variation between the direct and quadrature axis is fairly small in this machine as it is shown from the construction. So now coming to typically according to there is a very little less than 10% variation between the quadrature and direct axis inductance because it's mostly the typically the surface is covered by the magnets like. So the particular perfect has a kind of control, operation and characteristic of surface mounted palm magnet. So this is like a surface insert kind of palm magnet, how the magnets are inserted into the rotor, and this is typically the let's say photograph how the magnets are inserted, surface insert palm magnet machine with the typically there is the flux diagrams of this kind of magnet. And then the interior palm magnet brushless machine. Then you have there are various type of interior palm magnet machine especially used for EV industry. As you can see with the flux barrier where magnets are put, the machine geometry we have a saliency, a quite good saliency because we put a earth magnet which we have like air into the flux barrier. So quadrature axis is really have a high, you can call it the reluctance, high inductance and lower inductance is on quadrature axis. So it give a inverse saliency or you can call it inverse construction compared to the conventional synchronous machine like. And this is spoke magnet, the people really try for different kind and special direction magnetized with the rotor. Then the interior magnet with the damper bar for direct, you can call it line start motor, and then radial magnetized motor, the interior double layer magnet and hybrid magnetized rotor, then the interior double layer magnet and then hybrid magnetized motor, and then the typical interior palm magnet brushless motor rotor geometry, how it look like, and with the typically photograph how it look like with the magnet geometry here. So, and then the typical interior palm magnet brushless motor rotor geometry for different kind of electric vehicle from Pyrus 2003 to Pyrus 2010, Ford, Calvert, Honda Accord, then Camry and the Nissan Leaf. I mean, what kind of geometry really they have invention in last 15 to 20 years with very good power density, especially so that weight is reduced, and they are designing for high speed with the typically kind of field weakening and constant power characteristic. So interior palm magnet brushless machine. So interior palm magnet rotor construction is mechanically robust and therefore suited for high speed application. So manufacturing of this arrangement is more complex than the surface mount or insert magnet rotor. And note that the ratio between the quadrature and direct axis inductance can be higher than the insert magnet was generally in the range of 3, or even there has been a claims of much higher ratio up to order of 10 in interior palm magnet construction. And typically you can say interior how palm magnet brushless machine of this different kind of typically with the magnets on Q2D axis inductances like the surface mounted it is really maybe equal, but in this case it is typically AD less than LQ. I mean that is the invert construction we call it like, okay. And then interior so circumferential insert palm magnet rotor seems to require a large volume of the palm magnet, and therefore such as this configuration is not very suitable for high energy density palm magnet since they are expensive. According to this configuration can be only confined to low energy density and low cost magnets such as ferrite. Uniquely this configuration bestows the rotor arrangement that can build the higher air gap flux density than that of magnet gear. So it is achieved by the fact that the area of cross section of the magnets is much larger than the rotor surface that conduct the flux from magnet to stator, and because of it higher air gap flux density compared to say the surface mounted ferrite PMSM. This configuration is very desirable from the point of view of higher efficiency and smaller stator excitation for the same power output. But the higher air gap flux density is achieved at the expense of higher rotor volume compared to that of rotor with higher energy density magnet. And the insert magnet construction has the advantage of high mechanical robustness and high ratio between the quadrature and dielectric inductance, and many more arrangement of magnets on the rotor are possible, as they are rarely used generally in industrial fluxes. So, this is typical. So, the Indian permanent machines, but higher air gap flux density is achieved at the expense of higher rotor volume compared to that of rotor with higher density magnet. And the insert magnet construction has the advantage of higher mechanical robustness and higher ratio between the quadrature and dielectric inductance, and many more arrangement of magnets on the rotor are possible. They are very rarely used in general industry practice. So, there are interior magnet with this plug plot is shown here. You can just see the major space is given to stator and rotor have a very small space, and that provides certainly the high power for a particular size. So, the flux barriers that are at the corners of the magnet increase the reluctance and hence does not encourage the flow of flux line. Without these flux barriers, there will be significant leakage of the flux between the magnet, and these leakage flux line out skirt the stator electromagnetic circuit, and therefore the such leakage flux does not contribute to the any torque production and hence is a waste. One of the important point to observe is the surface and interior permanent machine is the flux in the rotor back iron does not change, and the stator is cylindrical except for the stator slot opening. So, if the stator opening are ignored from the electromagnetic point of view, then the rate of change of flux density in the rotor back iron is 0, hence the eddy current and stage loss are 0. And you can see finite element simulation showing the flux and flux density of interior permanent and surface mounted permanent brushless motor in two cases. So, the real situation is that there will be a variations in the flux from the magnet and its counter the stator slot and teeth with the resulting reluctance variation will change the flux and its density to extent in the back iron of the rotor, also resulting some core loss. In PM motors, the Hall back array, there is hardly any flux in the rotor back iron, and hence the iron loss in it can be avoided. So, typically PM Hall back array and uniform flux typically focusing. So, you can see how Hall back is really created in a manner that how the flux flows into different parts. So, a very special kind of geometry like. So, it is also practical to reduce the back iron thickness, and it has to carry very little flux and thereby reduce the rotor weight, resulting in a significant increase in power density and lower inertia for the machine. But this comes at the cost of fairly complex manufacturing of the rotor compared to the conventional surface mounted PM rotor. Coming to axial flux brushless machine, the mechanic machines are constructed that have a flux along with the axial direction of the shaft, and they are known as axial flux machine or package machine. Industry, as you can see that we have a machine with the stator between and rotor on both the side, or we have a stator core on both the side and the rotor is in between. The coils, how the stator coil looks like, it give a complete concept of geometry like. So, there are a lot of motors which are axial flux permanent kind of a disc motor. You can see size of the motor is quite small with the different parts, how really different parts are assembled, and the motor comes in form of the disc, require very less space. They are very suitable for EV industry, especially for the hub motors and many other applications also. They consider quite high power density motor like. The axial field motor also can be classified with the structure like single stator or single rotor, and then double stator single rotor or single stator double rotor or multi stack, like as you can see slotless or slotted motor and drum winding. The winding is also different kind of windings here, and ring winding. This is conventionally like used earlier in the people tried very early stage of this motor, same kind of concept is used in this. There are two mainly type of classification: axial flux motor with planar concentrated winding and toroidal winding. Typically in case of, so you can just see how axial flux machine have a different kind of winding and magnets arrangement like. So, there are two main types of classification of axial flux machine with planar concentrated winding, ACE typically if we talk about, and with the toroidal winding with the typically B and D, and normal winding rules also apply here. So, you can just see axial flux permanent machines how the winding is physically there, how it's animated portion is there with the winding, and typically the different parts of. Then the disc axial field motor with the PCB, very low PCB motors winding like them, and then the motor with the planar and concentrated winding. Then the axial field with the two sides of rotor is in between, or you have a straight assembly in between and rotor on both sides. And then the claw type, which is very popular for especially for the generator used in case of your automobile for charging the battery. It's a brushless construction, very high power density, very small space requirement, because space is a major problem typically for, as well as the weight is also important. And the disc motor used for alternator, typically where the magnet is a disc form in between. So I mean, there is no ferromagnet material virtually on the rotor. It's only disc of the synthetic bounded permanganate material, rare material. So you can call each of these machines can be considered as a stack of such multiple stacks and can be cascaded for increasing the power, and that is why they realized automobile industries in late 1960 for developing a line of various powertrains for various models, and such a concept has gained momentum again in 1990 for naval propulsion application, even in multi-megawatt range of power, and construction is much simpler in concept than in practice. So stator iron is laminated in the radial direction and the resembles considered rings that usually have a constant slot width and tapered teeth because of the magnets are pre-shaped and area of cross section faces the air gap close the radial direction, and such an arrangement of slots and teeth make the radial flux density in the teeth constant. So axial flux machine with the single stator and single rotor and single stator has the disadvantage of having attraction force between the stator and magnet. Even forces due to the magnet manufacturing tolerances there are mostly eliminated in the machine having two stator, one on each side of the rotor and one on the rotor vice versa. The machine with the single stator and rotor have a back iron in both, where the one of the two stator and one rotor has the back iron in the rotor but has a back iron on this. Because of the two stator, its power density is higher than the other machine, with because you can put more conducting material where the energy really going to be really generated or flowing like that. So the key to this machine's construction is the way of laminations are assembled, and it has presented a formidable problem over the years, but manufacturing solutions have been around to mitigate the complexity of manufacturing of lamination and the assembly. So unquestionably, the radial field machines are superior in simplicity of manufacture and assembly, hence their overwhelming popularity and presence in the marketplace. These are the typically comparison of different kind of permanganate rotor geometry, I mean, which I have shown in the, I mean, like typically with the advantage, limitations, and rating and applications like also. Now coming to permanganate and magnetic circuit. Now typically selection of permanganate, as you can see, either surface mounted motor or interior buried magnet. So permanganate have not been used for, was not matured until the mid of 20th century. So after the invention of helical and Faraday magnet, permanganate were used in DC machines in smaller power applications such as automobile auxiliary motors, and recently the improvement in the quality of permanganate material and the technical advances of the control method along the replacing induction machines, permanganate machines in many industrial areas. So magnetic behavior of permanganetes is described in terms of following three major quantity like remanence, and is also called residual flux density, the magnetization flux density remaining in the permanganate material after the saturation, and coercivity, the negative field strength necessary to bring the remanence to 0, and magnetic maximum energy density product indicate the maximum energy that can permanganate material can hold. So following the figure, typically BS curve for magnet material, which explaining BR and SC, as well as the total characteristic, how much is the energy density in second quadrant. Typically you get it for, I mean, the total energy density from the this characteristic. By applying a strong field on a permanganate sample, the material is to be initially magnetized, and then the setting of the field allows the material sample recoil along with the upper curve, and this curve assume a fixed and constant slope called permeability, and the BH occurs, Pmax occurs at the point where BH hyperbola is tangential to the recoil demagnetizing line in the second quadrant. You can see following tables show the unit of the each property like PR in Tesla, SC in ampere per meter, and BH curve in joules per meter cube, I mean, like also. So this is a major magnetic property of magnetic material. So temperature coefficient, the variation of the remanence in 1 degree Celsius increase in temperature is another important property for the design engineer in permanganate material, since some permanganate materials are very sensitive to temperature changes. And although manufacturing of permanganate started with a magnetic carbon steel from 18th century in London, the actual history of permanganate machines, PM machine on the individual basis started with the Enlico in the first half of the 20th century. For Enlico based on aluminum, nickel, cobalt and iron was replaced by ferrite in late 1960 because of Enlico have a high price caused by the complex manufacturing process. And in spite of its poor maximum energy density BH max, ferrite is still widely used in many applications today because of the abundance of raw material and the low production cost. And since ferrite is composed of fine particles made up from iron oxide Fe2O3 with barium Ba and strontium Sr. This magnet is popularly known used in complex shape. However, the ferrite is not suitable for high temperature application because of its high rate of decrease of Br and C with increasing temperature. And these are typically the BH curve for two ferrite magnets with the ferrite typically comparison with the temperature. So, the another is a typically ceramic cobalt is a rare earth magnet developed in late 1960. The cost and availability of this magnet of material limit its commercial success, but the good thermal stability allows its use in application exposed to high temperature like aerospace industry. After General Motors and Sumitomo simultaneously announced the development of neodymium or boron, this type of magnet became widely used in many industrial areas. So, for its high energy density capability, relatively low cost compared to ceramic cobalt, neodymium iron boron is the best material in applications requiring a small product size, and ceramium iron nitride SMFEN is the latest permanent material introduced in mid 1980. This material has the highest resistance to demagnetization, corrosion and temperature changes, which are the disadvantage of neodymium iron boron magnet. So, ceramic cobalt is the rare earth magnet material developed in 19 and the So, historical development of the permanent material throughout the 20th century is shown in next slide. The graph shows the improvement of the energy in the material by introducing new types of material except ferrite. So, ferrite does not have desirable value of this because of the increased coercivity of ferrite according to decrease in remanence. And this is the typically the characteristic of BH or energy density with varying in the different years how it is developed. And now you can say we have an neodymium iron boron after 1980 or 82, and probably the latest in 2010 it has a almost the energy density which is probably going to be around 10 times the ferrite magnet. So, now coming to selection of permanent, the flux density in the magnet material is used Bm equal to Bh plus Bi. The excitation component Bh is directly proportional to the magnet density H and given like Bh equal to mu0 H, and where H is the magnetic intensity. In all magnetic material, this component is very small compared to the intrinsic flux density. And combining about two equations, the magnetic flux density can be written as Bm equal to Bi plus mu0 H, where Bi is the intrinsic flux density, H is the magnetic flux density, and Bm is the flux density in the magnet, or known as a normal flux density in the magnet. A typical ceramic magnet, typically ferrite magnet, intrinsic and magnet flux density are shown in the next quadrant in the next slide. So, second quadrant is responsible for how the relation, how these two quantity Bi and Bm are expressed in this second quadrant characteristic of this permanent material. So, you can call it like with this characteristic, the magnetic flux density in the second quadrant is the straight line, and it can be represented Bm equal to Br plus mu0 mu rmh, and mu rm is the relative permeability of the magnet. It is seen that at H equal to 0, the intrinsic and normal induction flux density pass through the point known as dominant flux density Br. Like, so, intrinsic flux density in the second quadrant can be derived from the demagnetization characteristic of magnet as follows: Bi equal to Bm minus mu0 H and B, or equal to Br mu0 H in bracket mu Rm minus 1. So, for a hard magnet with a straight line demagnetization characteristic, note that the intrinsic flux density is constant, and second quadrant that it remains permanently magnetic, and this is termed as a high grade magnet. And as you can see, the characteristic BH characteristic of these, like, so if the demagnetization characteristic is not a straight line in the second quadrant, then the intrinsic flux density is not a constant, indicating the permeability of magnet is not as good as that of high grade magnets, and therefore such magnets are known as alloy grade magnets. The coercive force required to bring the magnetic intrinsic flux density to 0 is the intrinsic coercive force SCI, and that of normal flux density is the coercive force or coercivity. So, demagnetization characteristic is one of the used in analysis and design of machines, and it includes the effect of the external magnetic field intensity that invariably comes into the existence in the machine due to its binding excitation, and the material that retain magnetism are known as a hard magnet, and the ability to retain magnetism is found in cobalt, iron and nickel, and they are referred as ferromagnetic material. So various materials such as anlicophile, ferrite, typically ceramic, samarium cobalt and indium iron boron are available in permanganate for use in machine, and the most popular one in fact is the semi cobalt and indium iron boron magnet called rare earth magnet. General base characteristic for all these materials, indium iron boron, semi cobalt, ferrite and nickel, are shown here, and you can see that in indium iron boron we have energy density typically around 10 times than the ferrite magnets. So coming to demagnetization characteristic for available permanganate material in the market, the reader is referred to manufacturer data sheet that may be obtained from the manufacturer, and data will be available for complete BS characteristic in 4 quadrant of magnetic flux density versus magnetic flux intensity and not limited to second quadrant. And the last 3 listed magnets have straight line characteristic, where Alnico 5 has the highest remanent flux density but has nonlinear characteristic, and the flux density at zero excitation is known as remanent flux density. We are referred to as remanence also in some shown in figure next slide for the general PM. So as you can see, the BR is a remanent flux density here, and the different operating point on this characteristic like. So the low grade magnets has a curve usually termed as a knee at the low flux density, and around this point it sharply dives down to the zero flux density and reaches the magnetic field strength of Sc known as coercivity. And the magnetic field strength at the knee is Hk. If the external character acting against the magnetic flux density is removed, then it recovers the magnetism along with the line parallel to the original magnet BS characteristic, and in that process it reaches a new remanent flux density BRR, considering the lower than the original remanent flux density. So the magnet has intuitively lost a value equal to BR minus BRR in remanent flux density, and even though the required line is shown as a straight line, it's usually a loop, and the average of the looping flux density is represented by the straight line. And in case of high grade magnet, the BS characteristic is the straight line and its coercivity is represented by SCH, and the line along with which the magnet can be demagnetized and restored to magnet is known as the recoil line. The slope of this line is equal to mu0 mu rm as derived from the relationship between the flux density and magnetic flux intensity, where BURM is the relative recoil permeability for the high grade magnet. For semi cobalt and indium iron boron, the recoil permeability mu rm nearly has the value 1.03 to 1.11. Now coming to operating point air gap line, to find out the operating point on the demagnetization characteristic of magnet, consider the flux path in the machine as how it is the flux is flowing through the magnet N pole and S pole through the stator and air gap, simply out of the stator and layout of the machine. So you can call it the flux crosses the north pole and rotor magnet to stator through an air gap, then closes to the flux path through stator and rotor south pole via air gap, and in the process the flux crosses 2 times the magnet length and the 2 times the air gap. So MF provided by the magnet is equal to the MF received by the air gap if the MF requirement of stator, rotor and loss is considered negligible. So we can say here just with the approximation HM LM equal to HG LG, where HG LG are the magnetic field intensity or strength in magnet and air respectively. LM LG are the length of the magnet and air gap respectively. So operating flux density on the demagnetization characteristic can be found out BM equal to BR plus mu r mu0 BRM HM, assuming that it's a straight line. So air gap flux density in terms of its magnetic field intensity can be expressed BG equal to mu0 Hg, and substituting the HM in then substituting Hg in terms. So BM equal to BR plus mu0 BRM HM equal to BR minus mu0 Hg Lg upon Lm, and or equal to BR equal to mu RM Lg upon Lm mu0 Hg, or BR equal to mu0 Lg upon Lm into Bg, neglecting the leakage flux to Bg, considering the Bg equal to Bm. So operating flux density derived Bm equal to Br upon 1 plus mu Rm Lg upon Lm. So this clearly indicates that the operating flux density is always less than the permanent flux density because of the air gap excitation requirement. Note that the excitation requirement of iron and leakage flux are not neglected in this conceptual derivation. The equation gives design guideline, and consider the air gap flux density that is equal to remanent flux density to the magnet Bm equal to Br upon 1 upon plus 1 plus mu Rm Lg upon Lm. And in this case the denominator of the equation had to be one which amounts to thickness of the magnet being much higher than the product of the air gap length and the relative permeability of the magnet. So, approximating the relative permeability of the high grade magnet to be 1, the thickness of the magnet has to be much larger than the air gap length to equal to the air gap flux density to the magnet of remnant flux density. This results in a large magnet, which is not feasible in case of practical machine from viewpoint of cost and compactness of rotor and hence the machine overall. So, assuming the thickness of the magnets is far higher than that of air gap length, is not practical. So, this is another issue that makes it impractical. So, there will be a leakage fluxes between the magnets in the air gap without connecting the stator part of the magnet machine, and it will be significant when the gap between the adjacent magnet is smaller compared to the thickness of magnet. Therefore, the practical ratio encountered between the thickness of magnets and the air gap length it varies from 1 to 20. So, lower this ratio is the volume of magnets and cost will be lower, and so also the power output and power density of the machine. So, higher this ratio, the characterized described in previously are higher. Increasing the ratio does not lead to a proportional benefit in the power output, and beyond a certain ratio between them, the benefit be due to the factors such as leakage fluxes and increasing the volume and weight of the rotor, resulting in a lower power density of the machine. So, the operating point thus obtained is shown in the figure, and line representing the operating flux density BM and original known as air gap line, also known as load line, as you can see in the diagram. So, now the slope of this line is equal to the negative or a fictitious permeance coefficient mu c times the permeance of the air, and if the stator is electrically excited to produce the demagnetization, then the load line move towards the left and parallel to the line and shown in the figure. The operating flux density is further reduced from Bm. Note that the permeance coefficient is derived from the operating point Bm and Hm. So, Bm equal to Br plus mu 0 mu Rm Hm and or equal to minus mu c Hm, where Hm is the magnetic flux intensity due to the stator current excitation in the machine. So, the permeance coefficient can be derived mu c equal to minus Br upon mu 0 Hm minus mu Rm, but the remnant flux density Br can be expressed by assuming that there is a function of operating flux density flux intensity as Hm equal to Br equal to minus mu 0 mu Re into Hm upon as a function of Hm into Hm, where mu Re Hm can be considered as external permeability dependent on Hm. The permeance coefficient derived as mu c equal to mu R as a function of Hm minus mu R. So, the variation in the remnant flux density due to the temperature changes as well as the impact of the applied magnetic field intensity, both of which are induced by the external operating conditions, are clearly seen for this formulation of mu c. And as demagnetizing field is introduced by external operating condition, it is seen that the permeance coefficient will decrease as the external permeability also decreases from that operating point. So, in hard permanganate, the external permeability is in the order of 1 to 10 in the normal operating region, and it may be derived as it is in case of following. Consider an example with the high grade permanganate having a remnant flux density of 1.2 Tesla and coercive force of minus 9 into 10 power 6 ampere per meter. Let the air gap line produce a flux density of 0.8 Tesla. Find out the permeance coefficient. The relative permeability of the magnet has to be evaluated, which is obtained from mu Rm equal to minus mu R upon mu 0, and putting value it comes 1.058. The operating flux intensity for the operating flux density of 0.8 Tesla is Bm equal to Br plus mu 0 mu Rm Hm. Putting value, typically it comes like 1.24 equal to 1.045 Hm, from which mu Rm is coming 1.058, and using this value the permeance coefficient can be calculated mu c equal to 2.13. So, and likewise for operating flux density of 1 Tesla, the permeance coefficient is 5.32. As the operating flux density lowered to 0, the permeance coefficient goes to 0, and for higher flux density, the permeance coefficient increases, and the realistic operating points up to 1.1 Tesla is nearly 92% of remnant flux density, and it stays within the value of 10, which brings up the point that for high grade permeum, the permeance coefficient is in the range of 1 to 10, hence it may be used as an indicator of the magnet operating flux density. The energy of a PM in external space exists only if reluctance of the external magnetic circuit is higher than 0. So, if the previously magnetized PM is placed inside the closed ideal magnetic circuit, that is toroid, or this magnet does not show any magnetic property in the external space. So, in spite of the fact that there is a magnetic flux phi r corresponding to the remnant flux density Br inside the PM. So, you can see as PM permanent material previously magnetized and placed in alone in the open surface as shown in the below generate the magnetic field, and to stabilize here the stabilization of PM alone, PM with pole 2 and PM with the inside the external magnetic zone and PM with the complete external armature circuit. So, to sustain a magnetic flux in external open space, an EMF developed by the magnet is necessary. So, the state of PM is characterized by the operating point K on the demagnetization characteristic as shown here. So, diagram of PM finding the origin from the recoil line and operating point. You can call it the location of the point K is at the intersection of the demagnetization characteristic with the straight line representing the permeance of external magnetic circuit open space. So, C external equal to phi K upon Fk, the tan alpha external equal to phi K upon phi r, Fk upon Fc, or equal to G external Fc upon Fr, where F represents the MF. So, the permeance Gsk correspond to the flux phi, MF correspond coordinate system and referred to as MF at the end of the permagnets, and the magnetic energy per unit produced by permagnet in the external space is Wk Bh Hk by 2, and this energy is proportional to the rectangle limited by the coordinate system and line perpendicular to the phi and F coordinates projected from the K, and it is obvious that the magnetic energy is Vk equal to Vm and Hk equal to H max. So, if the poles are furnished with the pole 2, the permeance of the external space is increases. So, the point which characterizes the new state of the permanent move to along recoil line from the K to point A, and recoil line K Gm is the same as the external internal permeance of the PM. So, Gm equal to mu recoil mu omega m Lm divided by Hm, or mu m equal to Sm upon Hm. So, the point A here in the diagram as shown in the intersection of recoil Kgm and the straight line OGA representing the leakage permeance of the PM with the pole 2. So, Ga equal to phi upon Fa and del tan alpha A equal to GAFC upon phi r. So, energy produced by permanent in external space decreases as compared to with the previous case, W equal to BAHA by 2. So, next slide is the space placed to PM in external electromagnetic circuit resulting permeance is G equal to phi upon Fa or tan alpha A equal to G upon Fc upon phi r, which means the coordinate Gp is much greater than Ga, then much greater than G external. So, for external magnetic circuit without electric circuit carrying the armature current, the magnetic state of the PM is characterized by the point, that is intersection of the recoil line Kgm and the permeance line OGP, where the external magnetic circuit is furnished with the armature winding, and when this winding is fed with the current that produces MF magnetizing the PM, the magnetic flux in the PM increases to volume phi n, and d axis MF FAD of the external armature field acting directly on PM correspond to phi n. So, magnetic state of the PM is described by the point n located on the recoil line of the right hand side of the origin of the coordinate system. Typically, to obtain this point, it is necessary to lay off the distance OF dash and to draw a line GP from the point FAD inclined towards the angle alpha p to the F axis, and the intersection of recoil line and the permeance line give the operating point N. And if the exciting current in external armature winding is increased further, the point N will move further along the recoil line to the right up to the saturation of the permanent. So, when the excitation current is reversed, the external armature magnetic field will demagnetize the magnet. For this case, it is necessary to lay off the distance OF dash AD from the origin of the coordinate system on the left, and the line GP drawn from the FAD with the slope will intersect the demagnetization curve at the point K. This point can be above or below the point K for the permanent alone in the open space. The operating point K is the origin of new coil line K dash GM dash. Now, if the armature exciting current decreases, the operating point will move along with the new recoil KGM K dash GM dash to the right. And if the armature current drops down to 0, the operating point takes the position PM dash intersection of new coil line G K dash GM dash with the permeance line GP drawn from the origin of the coordinate system. and owing to the basic following figure, the energy is as follows: WP equal to BP HP B dash HP dash by 2, or WP equal to BP HP, and where the WP is much less than WP dash is much lesser than WP. Diagram PM, finding the origin of recoil and operating point. So PM operating diagram, the location of origin of the recoil line as well as the location of the operating point determines the level of utilization of energy produced by PM, and PM behaves either in different way than DC electromagnet. The energy of a PM is not constant, and if the permeance and exciting current of the external armature change, so the location of the origin of the recoil line is determined by the minimum value of the permeance of the external magnetic circuit of the demagnetization action of the external field. So to improve the property of PM permagnets independent of external field, PM are stabilized, and stabilizes means the PM is demagnetized up to a value that is slightly higher than the most dangerous demagnetization the field during the operating of a system when the PM is installed. So in magnetic circuit with stabilized PMs, the operating point describing the state of PM is located on the recoil line. Coming to energy density, the energy density the magnet is found by taking the product of its magnetic field strength and operating flux density. This measure serves to differentiate the magnets used in machine with those having a higher value of preferred high power density machine, and the peak energy density point is the optimal from the point of magnetic utilization. The magnetic energy density Emax for hard red PM shown in the next slide and derived here as follows. So this is what on operating maximum BH, this we call it BH maximum line, energy product and preferred operating characteristic. So the energy density M in terms of the product of magnetic flux density BM and its intensity, field intensity HM, is found, and then taking its derivative with respect to the field intensity, equating it to 0 gives the condition that leads to magnetic maximum energy density. So step to find out the energy density, M equal to BM HM equal to BR plus mu 0 mu RM HM upon HM. So taking derivative of this energy density dm upon dh equal to 0, so it comes BR plus 2 RM mu RM HM. So from which we can find out the field density HM equal to minus BR upon 2 mu 0 mu RM, and thus the magnetic energy derived as E max equal to minus BRM square upon 4 mu 0 mu RM. Using above equation, the flux density at which the maximum energy density available found to be half of the remnant flux density, that is 0.5 BR. So the operating line for this flux density is shown in the figure giving the required magnetic strength. Note that this operating point for flux maximum energy density require a considerable amount of magnetization field strength from the stator excitation of the machine. Moreover, it is not practical to maintain this operating point in a variable speed drive, machine drive, as the stator current will be varying widely over the entire torque speed region. So to read energy density, the projection of BH curve or H on H curve is constructed as the energy to be negative. As you can see here how the typically, so for low grade PM such as Alnico, the magnetic flux density and energy density characteristic are shown here. As you can see typically as an electromagnet. So energy density comes from magnetic energy density is higher than the half of the remnant flux density in contrast to the higher grade permanent material characteristic. So maximum energy density is around 1/10 of the high grade magnet energy density to be observed. Therefore, the high performance application requiring a smaller motor weight and volume, these magnets are not preferred for use in electromagnetic devices. So now coming to energy stored in the magnet, the energy density give an indication where the best to operate the magnet in the device, but is not the same as the energy stored in the magnet. So from fundamental electromechanics, energy stored in the device is given Wm equal to volume and the integration H into B. So on energy stored in per unit volume is given Wm upon volume, that is the integration H into dB. So for example, consider a high grade magnet with the linear demagnetization characteristic, and that for the energy stored per unit volume Wm upon volume, that is 0 to Br H dm, or 0 to Br B minus Br mu 0 mu Rm dB, or minus Br square upon 2 mu Rm, or 2 Bh maximum, or 2 Emax in joule per meter square. So Bh max is nothing but maximum energy density and denoted as E max. Now coming to now magnet volume. The volume of magnet embedded in the rotor determines the single most important cost component of the permanent machine. particularly in case of higher power density magnet machine. It is critical in all applications to minimize the volume of the magnets, among other things, to minimize the cost of the machine as well as to have the smaller and lighter rotor. So magnet volume is found in terms of operating energy density and air gap volume as follows. So substituting Hg for in terms of Bg, so Bglg equal to minus mu0 HmLm, where the Bm Am equal to Bglg. So using these ideal characteristics, the magnet volume is derived as Bm equal to Mlm equal to minus Bgag upon Bm, or Bg upon mu0 Hg, or B square Aglg upon mu0 Bmhm, or equal to Bg square Vg upon mu0 Bm, where Vg is the air gap volume, Am is the magnet operating flux density, and Me and Ag are the magnet and air gap area. So note that the equation is framed in absolute magnitude of the energy density by factor of minus Hm as the positive value with the absolute sign, and from this relation it is inferred that the magnetic maximum operating energy density point of the magnet will yield the magnet with the minimum volume and hence the minimum cost. So this is simplified relation, since the leakage flux between the magnets is ignored and even the result is not far from the really preliminary design calculation. So thicker magnets give the higher flux density and thus more torque per ampere. However, higher flux density also mean higher core loss. So thicker magnets give the lower inductance, faster response, but higher pendulum current ripple. And these thicker magnets make the motor more resistance to demagnetization, and thicker magnet also increases the cost significantly. So doubling the thickness will typically only give 5 to 10% more flux. So the magnets can be individually made in many shapes and sizes. So they also come with the ring form. The ring form is the easiest to install, as they can be slided on the top of the steel laminated rotor and held in the place of suitable means. Then they can be magnetized in any desired direction. So the disadvantage of ring magnets is that they are expensive compared to the individual magnets. So individual magnets can take any shape. So each pole may consist of number of magnet segments instead of one piece. So reason for this is that the large machines with constraint on the machining of the magnet material also charging them to magnetize, and the use of single magnet piece or segmented per pole may not be possible, or if possible it may not be most economical. So in some cases a single magnet per pole is not suitable for large flux weakening range of the operation. So it is found that the flux weakening capability is enhanced by multi-segment magnet per pole structure. They can also be stacked one on the top of another with equal or varying width to yield the desired flux distribution, such as sinusoidal or trapezoidal distribution in the air gap of the PM, synchronous or permanent brushless DC machine respectively. And the three kinds of magnet poles are in the next. So you can say the magnet may have varying thickness and width for stacking up, and note that the magnetization polarity are in the same direction, as you can see in a relation of three types of magnets, I mean with the stacks and with the different pieces and single piece like. So all the arrangement of the permanent, all the three arrangement have advantage and application. So single magnet per pole is ideal for a small machine. However, pole machines may use multi-segment magnets per pole and the stacked pole structure. Single magnet and multi-segment magnets are prevalent in practice. So various shapes of magnets that are in practice, such as rectangular, radial and bread loaf, are shown in next slide. So radial and bread loaf types of magnets are ideal for surface mounted type of PMS. So as you can see how it looks like, various type rectangular, radial and typically the bread loaf. So the air gap in case of the radial magnets on the rotor surface is uniform, assuming that it is not partially embedded in the rotor laminations, with the result that air gap flux density is uniform. So radial magnet can come with their end surface being radial or parallel, and accordingly they are referred as surface radial and surface parallel magnets, and they are shown in the next slide. As you can see here, radial magnet, surface radial magnet and the surface parallel magnet. So now the air gap and the bread loaf magnets, for the bread loaf magnet is uniform, and hence the air gap density also being non-uniform. So that allows the shaping of flux density in the air gap, which can be other than rectangular and constant over the magnet arc. So rectangular magnet commonly used interior permanent construction. The recent trend is to have multiple magnets per pole in the construction to facilitate higher field weakening region of the operation. and this is structure not ideal for in surface mount machine as the desired constant air gap cannot be maintained. So constraining factors in this regard shapes are as follows: the minimum material per magnet pole, ease of machining and construction, plug density distribution that is rectangular or sinusoidal, and because of these constraints, many shapes have not been seen in light of the day. So magnet are magnetized with the constant certain orientation or direction such as radial, parallel or any other direction. So magnetization and rotation strongly influences the quality of air gap flux density distribution and indirectly affect the power density in the given arrangement of the machine with PM, and the air gap flux density distribution influences the turn further harmonic torque generation in the machine, and the presence of harmonic torque corresponds to the quality of torque output in the machine, particularly in case of high performance motor drive. So the typically radial and parallel magnetization. So radial and parallel magnetization are shown here. The normal direction of surface indicated by vector n and the magnetization vector by m. So magnetization of radial magnetization and then the parallel magnetization. So the radial magnetization along with the radius, while the parallel magnetization parallel to the edges as in case of surface magnets, but that need not to be true in case other edge shape. The key in that case is the magnetization direction in horizontal, and the effect of the two such magnetization is the synchronous machine shown in the form of air gap flux density versus rotor position using Farad element analysis as flux poles in next slide for a machine of 24 slot 2 pole. As you can see how it looks like, and the versus the rotor position radially parallel to the typically with the parallel magnetizing and radial magnetizing. Radial and parallel magnetization. The radial magnetized produce a rectangular flux density distribution in the air gap, where the parallel magnetizing magnet produce the sinusoidal air gap flux density distribution. The reason for this flux distribution can be explained in the following. The magnet flux leaves the magnet and enters the stator in the normal direction to their surface. So the flux density vector is radially magnetized magnets in normal along with the radial direction itself, resulting in the magnetic flux density flowing in the radial direction also. So therefore the air gap flux and its density are maximum and remain uniform constant across the magnet. And in case of the parallel magnetized magnets, the normal component of the flux density vector that enters the stator iron can be seen to be proportional to the sine of angle between the x-axis and the magnetization vector m at that point in the magnet, with the result that the flux density is sinusoidal in the air gap. So there is also a tangential component of flux density in the case of parallel magnetizing component magnets embedded in machine, while it is 0 in the radial magnetizing machine. Coming to the Hallback array, so there is also case where the magnets need to not to be magnetized in radial and parallel direction, but can be also in any direction, such as magnetization exploited by arrangement due to Hallback. So radial or parallel magnetization requires a back array for better utilization of magnets, and these are all cases when there have been illustrated so far. So they are also the most prevalent in practice since they are much easier to realize. So here is the Hallback array. You can see radial magnet array in the air. So before Hallback arrangement is considered, the radial magnet arrangement is considered again here for plane magnet arrangement or array in air and is flux path shown in next slide. So note that the magnets are of alternate polarity. To magnetize magnetic utilization, iron is required on both the top and bottom of the magnet arrangement, and in the machine one side of the magnet array faces the stator, the air gap, and the other side the rotor lamination. Both stator and rotor have a steel lamination. So Hallback arrangement, sometimes known as Hallback array, shown below here the combination of the two magnets array, one radial magnet array and another azimuthal magnet array. You can see here a whole Hallback radial magnet array, azimuthal array, and then finally the typically Hallback array magnet like. This Hallback, the combination is made such a way that the succeeding magnet is combined with the Hallback array have either clockwise or counterclockwise magnetization, and its flux distribution can be arrived at by summing the flux distribution of the radial and azimuthal magnet are shown in the next slide. So as you can see here how the different radial magnet, azimuthal, and finally the Hallback magnet flux distribution in Hallback. So a finite element flux plot of Hallback array with a several magnet segment is shown here, illustrating that the simplified conceptual flux plot fairly correspond to relative. There are some flux lines seen on the top of the magnet array, and they are very small compared to the number of flux lines at the bottom of the magnet array, and hence they could be constructed by negligible on the top and almost all being the on bottom of array. This is how the flux flow of Hall array with 7 segment magnets. So from the flux distribution of this array, the following observation are made. There is almost no flux at the top of the magnet, implying the back RN is not required for this ideal Hall array. The flux is much more focused, that is in radial magnet array, and could be focused in direction of depending upon the magnetization of the magnets and the number of magnet segment that make a pole. So third, the flux is downward interior or upward exterior depending upon the orientation of Hallback magnet segment. Clockwise orientation of north and south poles of the magnets give upward flux distribution of conventional machine with the stator and rotor outer, and similarly anti-clock rotation of the magnet polarity with the inward flux distribution. This is preferred for magnet line with outer rotor and known as inside machine industrial circle. So this is a Hallback array correspond to the case 3 as shown here, typically for outside flux distribution with Hallback, and this is the inward flux distribution with Hallback array. So here it is shown the air surrounding the magnets array rotors to get the glimpse of the flux distribution, and there are hardly any flux line outside and inside of the magnet array, and all the flux is connected in the inside and outside respectively for the above two rotor, and a small amount of leakage flux evident in the simultaneously, and it is usually negligible compared to the total flux on the significant of actively side of the array. So here it is shown that air surrounding the magnets array rotors to get a glimpse of the flux distribution, and there are hardly any flux line outside the or inside the magnet array, and all the flux is concentrated in the side and outside respectively for the whole two rotors, and a small amount of leakage flux is evident in the simultaneous simulation, and it is usually negligible compared to the total flux on the side of active side. And this is typically the same rotor Hallback magnet array inside the outside stator synchronous machine are shown below here with the air gap flux density distribution as a function of rotor assembly. And this is the inside the Hallback magnet array rotor in the machine and air gap flux density distribution. So from the above figure, it becomes obvious that the leakage flux remains at the lower level on the inactive side of the Hallback array rotor, and almost all the flux is concentrated on the side facing the stator, and leakage flux, even though small, is not particularly desirable in case of the outer rotor machine, and measures to curb them to have the restored in such cases. And the flux density distribution is almost sinusoidal for rotor with the 4 magnets segment per pole. So the machine with the inner rotor has lower flux density level compared to the flux with the outer rotor, and this is being caused by the stator slots and system, particularly as it. So Hallback magnet array are realized in two ways: the use of discrete magnet segment or blocks of magnetic material that are uniformly magnetized in the desired axis or direction of appropriate Hallback, and use of Hallback ring magnets using centered or mounted forms of orientation in NdFe powder during the injection molding process and pulsing magnetic them with the required Hallback field distribution. So the air gap flux density distribution of the inner Hallback rotor magnet arrangement is compared with the pairing thickness and showing here. So the distribution for increasing the magnet thickness. So the flux density distribution is almost sinusoidal when the ripples due to the slot opening of the laminations are ignored, and with the higher number of magnet segments per pole, the flux density distribution is expected to be much more closer to the sinusoidal. So the features of Hallback can be summarized as focusing the flux at the heart of the Hallback array, and pure sinusoidal distribution for a Hallback array, but not possible to realize in practice. Higher magnetic potential of the fundamental 0.41 4 times the conventional experiment is linear motor is theoretically 1. This does not translate into 41.4% flux in the practice due to non-ideality to cylindrical environment and rotor construction. Estimate is for rotating BMSM proved to be previous point. So further positive no back iron is required as flux hardly exists on the one side, and the Hallback array can be bonded directly to the non-ferrous substrate such as aluminum or other material with good structure property. Since the central field distribution exists, there is no torque ripple. The skewing of the stator rotor magnets are avoided, which is major saving in the manufacturing operation. So Hallback array leads to high performance positioning application because of non-zero Cogging torque, and it is found that the cogging torque is reduced in a Hallback magnetic machine to almost 20% of that of conventional magnet machine. And in spite of some of the unique advantage, this magnet array is yet to be explored in commercial application due to its complex construction and magnetization of PMS. Now coming to numerical problem. So starting with question 1, the magnet is stabilized at minus 35 kiloampere per meter with a remunerated flux density. The relative permeability of iron is considered very large, so the reluctance of iron is 0 to simplify calculation. Find the current in the coil required to operate the magnet at its stabilized operating point. The data for the device are air gap length Lg equal to 0.5 millimeter, PM thickness Lm equal to 12 millimeter, leakage factor K equal to 1.25, magnet area equal to air gap area, and number of turns in the coil is TPH equal to 1000. Now coming to the solution, the magnetic relative permeability is found from the characteristic by considering the Riemann flux density and another operating flux density B1 H1 as mu Rm equal to Br minus B1 divided by B mu 0 H1, and putting the value it comes 2.665. As the magnet is stabilized at Hd equal to minus 35 kiloampere per meter, which gives the magnet operating point Bm equal to 0.7856 Tesla. And new remanent flux density is to find by drawing the required line, which is the line parallel to the magnet characteristic from the operating point or analytically obtained form Bm equal to Brr plus mu 0 mu Rm Hm. And therefore, the new remanent flux density for the stabilized operating point is Brr equal to Bm minus mu 0 mu Rm Hm, and putting value it comes to 0.9028 Tesla. The operating point of the magnet with no external excitation in the device is obtained from B0 equal to Brr divided by 1 plus mu Rm Lg upon Lm Am upon Ag into 1 upon K, and putting value it comes 0.8291 Tesla. Now, the fictitious coercivity of the magnets in low grade magnet is SC equal to Brr upon mu 0 mu Rm, that comes to 65.5 kiloampere per meter, and the flux density lowered by external excitation is 0 delta B equal to Bm minus B0 divided by V0, and putting value it comes minus 0.05246 Tesla. The external field strength required to demagnetize the magnet is H equal to minus delta B into SC, and putting value it comes minus 14.14 into 10 power 3 ampere per meter. Now MF to create this flux, this field strength is given by F equal to He into Lm, and putting value it comes minus 169.68 ampere turn, and the flux density lowered by external excitation, that is I equal to Fe upon TPH, and putting value it comes minus 0.16968 ampere. Now coming to the question 2, the electromagnetic device shown below is considered for this problem. The magnet is of the neodymium variety with the remanent flux density of 1.1 Tesla and coercivity of 0.86 into 10 power 6 ampere per meter, and has a straight line demagnetization characteristic. Determine the flux density in the air gap when current in the coil is 10 ampere. The data for the device are given same as in numerical 1. Air gap length equal to Lg equal to 0.5 millimeter, PM thickness Lm equal to 12 millimeter, leakage factor K equal to 1.25, magnet area equal to air gap area, and number of turns in the coil equal to pH equal to 1000. Now this is the typically the configuration of electromagnetic device used in numerical 2, where the magnet is put of Lm length with the flux density in Bm, and there is a length of air gap Lg with the of course turns with the on same electromagnetic device with the current I with the TPH. Now coming to the solution, the flux density Bm equal to Brr plus mu 0 mu Rm Hm. So, and at B equal to 0, S equal to Sc equal to 0.87 into 10 power 6 ampere per meter, which on substitution give to the relative permeability of the magnet as mu Rm equal to mu R upon mu 0 Sc. Putting value it comes 1.0062, and the no load operating flux density B0 is obtained from B0 equal to Br upon 1 plus mu Rm Lg Am divided by Lm Ag K. Putting value it comes 1.0643 Tesla. The line connecting origin and no load flux density give the air gap line or no load line. To evaluate the load operating flux density, a line parallel to the air gap line shifted from the origin to the left of by an amount equal to the external field strength Hg had to be drawn to intersect the demagnetization characteristic of the magnet, and the external field strength is computed as follows. The external field F equal to TPHI equal to minus 1000 into 4, that's minus 4000 ampere turns. So now, as from the diagram, the external field strength is H equal to F equal divided by Lm, and putting value it comes minus 0.333 into 10 power 6 ampere per meter. So drawing the load line parallel to the air gap line from He intersect the magnet demagnetization characteristic yielding the magnetic flux density Bm as the 0.6575 Tesla. And analytically, the magnet load flux density is found Pm equal to 1 upon 1 plus mu Rm Lg Am upon Lm Agk in bracket Br plus mu 0 mu Rm Tphi divided by Lm, and putting a value it comes 0.6575 Tesla. And note that the air gap flux density is equal to Bg equal to Bm upon Am into K in Ag, and it comes 0.526 Tesla. Now coming to question 3, consider a magnet with pole face area Am equal to 625 millimeter square and the length Lm equal to 8 millimeter, and suppose Br equal to 1.1 Tesla and mu recoil equal to 1.05, and determine the flux density in the air gap and the magnet and the permeance coefficient. The solution is remanent flux phi r equal to Br into M, and that comes 685.5 microweber, and the internal magnet permeance is PMO equal to mu 0 mu recoil Am upon Lm, putting value it comes 1.0308 into 10 power minus 7 Weber per ampere. Suppose the air gap area is Ag equal to 700 meter square with the effective gap length Lg dash equal to 0.75 mm, and giving Lm upon Lg equal to 11.4, which is quite high value. So air gap reluctance is Rg equal to Lg dash divided by mu 0 Ag, putting value it comes 0.7958 10 to the power 6 ampere per Weber, and giving Pm 0 Rg equal to, putting value equal to, that comes 0.08203, and suppose the leakage coefficient of G equal to 0.95 typically for surface mounted PM. So air gap flux is phi g equal to F Lk phi r divided by 1 plus FLK PMO Rg. So putting value it comes 0.88272 phi r, and the normalized leakage permeance PR1 equal to 1 upon FLKG minus 1 divided by PM ORG. So it's 0.6416, and the flux density in magnet phi m equal to phi g upon FLKG. Putting value it comes 0.92918 phi r, and the air gap flux density Bg equal to phi g upon Ag, and putting value FLG into M Br divided by Ag plus 1 into 1 plus FLKG BM Rg, and that becomes equal to FLKG equal to phi r upon divided 1 plus FLKG PM ORG into Ag. So it comes 0.88 Tesla. Now the magnetic flux density is Bg equal to phi m. Magnetic flux density in the air gap equal to Bg equal to phi m upon Am. So it comes like 0.92918 phi r upon Am equal to 0.86696 T, and in the example Bm upon Br equal to 1.0221 divided by 1.1, so that is 0.92918. Therefore permeance coefficient is equal to mu recoil of Bm upon Br divided by 1 minus Bm upon Br, so it comes 13.776. Now coming to fundamental theoretical questions. So what is the basic operating principle of palm magnet brushless DC motor and how it differs from traditional brushed DC motor? A palm magnet brushless DC motor operates on the principle of rotating magnetic field generated by the stator windings to drive the rotor, eliminating the need for brushes, and this design enhances efficiency and reduces maintenance compared to the traditional brushed DC motor. So question 2, what is the selection of palm magnet material crucial in the design of brushless DC motor, and how do different material impact motor performance? Selection of palm magnet material such as neodymium or ferrite is crucial, and these magnet impact motor performance by influencing factors like magnet flux density, coercivity, and temperature stability. Now question 3, discuss the significance of back EMF in the brushless DC motor and design how it influences the speed, control, and efficiency. The back EMF is the voltage generated in the motor winding due to the rotor movement opposing the applied voltage. higher the back EMF at increased speeds limit the current, and hence consequently the speed contributing to efficiency. Now question 4, compare and contrast the various commutation strategies used in permanent brushless DC motors, including the sensor based and sensorless method. The commutation methods include the sensor based Hall effect sensors, and sensorless means using algorithm to determine the rotor position, and sensor based methods offer accuracy but may require maintenance, while sensorless method enhance the reliability but may sacrifice the precision. Now coming to question 5, explain how the torque and power output in a brushless DC motor are influenced by factors such as current, magnet field strength and motor geometry. The torque and power depend on the motor current, magnetic field strength and geometric design parameters, and increasing current or optimizing magnetic field strength enhances the torque and power output, but there is a trade-off with heat generation. Now question 6, discuss the challenges associated with thermal management in the design of permanent brushless DC motors and the technique employed to prevent overheating. So thermal management is the vital to prevent motor overheating. So technique include proper cooling, efficient heat dissipation material, and design consideration for minimizing heat generation in high current areas. Now question 7, elaborate on the concept of sensorless control in PM brushless motors and alternative methods for position sensing in the absence of traditional sensor. The sensorless control rely on algorithm to estimate rotor position, and simpler alternative for position sensing route the back EMF or flux, zero crossing detection and observer based method, and challenges include accuracy at low speed and during starting. Question 8, they examine the phenomena of demagnetization in permanent brushless DC motors and how can the motor reliably be enhanced in the face of potential demagnetization. So demagnetization occurs when the permanent loses and its magnetic property either due to the temperature effects or against an external opposing field, and design consideration appropriate PM sizing along with the operating with the temperature limits and current limits, armature field, and as the motor reliability. Now coming to question 9, explain the significance of magnetization curve in the context of permanent materials of brushless DC motors. Magnetization curve illustrated the relationship between the magnetic flux density and the magnetic field strength, and coercivity represent the material resistance to demagnetize, as shown in the figure as soft ferromagnetic material and hard magnetic material. Now question 10, elaborate on the concept of anisotropy in the permanent material. How does the anisotropy contribute to the directional dependence of magnetic properties, and why it is essential in the design of brushless DC motor? So anisotropy refers to the directional dependence in magnetic material property, and in permanent material, anisotropy is crucial for aligning magnet domains, optimizing magnetic performance in the specific direction, and trailing anisotropy ensures efficient utilization of magnetic flux in the motor's desired direction. Now coming to question 11, discuss the challenges and benefits associated with exploring rare free permanent materials for brushless PM motors. The rare free magnets such as ferrite or alnico alloys are explored to reduce the dependence on expensive rare materials. Challenges include the lower energy product and coercive compared to the neodymium iron boron. Now question 12, explain the concept of magnetic aging in permanent material. How does it occur over time, and what impact does it have on the long term performance and reliability of permanent brushless motors? Like magnetic aging involves changes in a magnetic property over the time due to the various factors, and it may result in reduced remanence and coercivity affecting motor efficiency, and proper design consideration and material selection aim to minimize the effect of magnetic aging. These are the typically books and references starting from the books by Kenjo and Nagamori in 1962 and 1986, and the latest book of typically here of 2010 by Ramakrishnan and by Professor Girgyas. And thank you.